Today we are going to talk about the large signal analysis of the MOSFET differential pair. So this is going to be very similar to what we did in class on Monday, except obviously now we're going to be looking at how the MOSFET version of this circuit behaves. So our general differential pair circuit for MOSFETs is going to look something like this, where we have some drain resistance RD through which a drain current of ID1 flows. We're going to measure the quantity Vout1 here at the drain terminal of transistor M1. And we apply our input signal VN1 here, which gives us our gate source voltage VGS1. And we're going to mirror this circuit on the other side. So here we have RD, a current, ID2. Here's the quantity Vout2. Here is transistor M2, where we are applying VN2. Here's the quantity VGS2. So again, we're starting with two common source amplifiers in parallel. And we finish things off with a tail current, ISS, like so. All right, so let's talk our way through things, much like we did in class on Monday. If only a common mode signal is applied to the inputs, what is happening with our drain currents, ID1 and ID2?
They are equal and they're both half ISS.
Exactly right. We know that our VGS voltages, VGS1 and VGS2, must also be identical to each other, right? Because the transistor M1 is carrying half of ISS and transistor M2 is carrying half of ISS, and transistors M1 and M2 are identical or are perfectly matched. Then we know that VGS1 is equal to VGS2, and we are going to call that quantity VGS minus VTH equilibrium. And this is going to pop up again. So VGS minus VTH equilibrium will be equal to the square root of ISS over mu n Cox W over L, where we are assuming here that our differential pair is sized in such a way as to make the channel length modulation coefficient very small or effectively zero. So whenever we have an input common mode signal, this is how VGS behaves. To ensure that transistors M1 and M2 stay in saturation, which means that VDS, which is just our output voltage here, measured with respect to this common source terminal, that quantity has to be larger than this guy, right? Because VDS needs to be larger than VGS minus VTH. So that tells us that our common mode voltage, VCM, is bounded. It must be less than or equal to VDD minus 1/2 RD times ISS plus a threshold voltage.
What's the subscript on that that current in the square root thing in the numerator?
SS. This guy right here, the tail current source.
What is VCM?
Common mode voltage. So
Got
CM, common mode. So we can't apply a DC common mode signal any larger than that constraint. If we do, we wind up pushing our transistors M1 and M2 out of saturation and into the triode region. All that's really going to happen there, like the circuit's not going to explode or anything like that. It's just going to behave very, very poorly as an amplifier because the transconductance we'll see is going to go down because transconductance in the triode region is significantly smaller than transconductance in the saturation region. So it's not going to cause any huge effects or anything other than it's not going to perform particularly well as an amplifier because it's operating in the wrong transistor mode. All right.
Current I.
SS.
Okay, sorry.
There's an SS here. It is an SS here. Or I'm using the double subscript SS because it's connected to two sources.
Next to the RB, ISS. Right?
This is also ISS. There is no IGS
Okay,
on
that's
this.
what I was confused.
Okay.
I was
All right.
thinking,
Let me rewrite this.
I'm sure we were referring to like the current passing through the circuit, but this is the total sum of the current passing through the circuit.
Right. So right here, the factor of 1/2 is coming from the point that
They're equal. But
exactly right. Yeah. So that's limiting our constraint. Yeah. So there. To be clear, I apologize for my terrible penmanship. There is no IGS anywhere on the screen at present.
it doesn't exist.
All of the I and then subscripts are SS, referencing this independent tail current source. Okay. All right, so our common mode operation is fairly straightforward. Our differential mode operation isn't particularly difficult either. So if Vn1 is much greater than Vn2, or another way to put this is that we have a large positive differential mode voltage, what do we expect to happen? So if Vn1 is large, VGS1 is large, which means ID1 is large, which in turn pushes this output voltage down, right? Pushes it further away from VDD. On the opposite side, if Vn1 is large, that means VGS2 must be smaller because this current has reduced, right? As ID1 goes up, ID2 must go down because they have to add together to make ISS. As ID2 gets smaller, the voltage drop over RD gets smaller, and the output voltage here at Vout2 goes up. So we still have that same teeter-totter configuration for our voltage, right? So if we push this voltage down, this voltage gets pushed up, or if we steer more current this way, then this current has to get smaller. We have constraints on things, right? Obviously, if Vn2 is larger than Vn1, the exact opposite case occurs. When Vn2 is larger, it's carrying more of the current, which makes this output voltage smaller. M1 is carrying less of the current, which makes this output voltage bigger. And so we still have that same teeter-tottering or seesaw operation. So now that we have a basic idea of what's going on, let's complicate things once again with math. All right. So the only changes that I'm going to make here, and it's the exact same change I made last class, is instead of considering VN1 and VN2, I'm going to look at VN1 as being 1/2 of VID and VN2 as being negative 1/2 of our differential mode voltage. So we're neglecting the effects of any common mode signal because we know exactly how that behaves. Now we're only looking at what's going on with the differential mode signal applied. Let's see, our goal here ultimately is to find our output differential mode signal, VOD, as a function of our input differential mode signal. And we need to find how to express the quantity delta ID as a function of our input differential mode signal as well. And as a brief couple of identities that we're going to wind up using here, we know that in saturation, the drain current for our transistors is going to be 1/2 mu n Cox W over L times VGS minus VTH quantity squared, where we're ignoring the effects of channel length modulation. And I am going to lump all of this part together right here as an arbitrary constant K so that I don't have to rewrite it over and over and over again. Okay. Similarly, our gate source voltage can be rewritten as VTH plus the square root of ID over K, which is simply the manipulation of this particular equation. All right. Okay, so getting into our analysis. V out 1 is obviously simply VDD minus RD ID1, and V out 2 is simply VDD minus RD ID2. So combining these two results, we can find that VOD, our output differential mode voltage signal, is the difference of V out 1 minus V out 2, which is simply negative RD times ID1 minus ID2, or negative RD times delta ID, where delta ID here is simply the difference between our drain currents. Very similar to what we did on Wednesday. Our next step is going to be similar as well. We're going to apply Kirchhoff's voltage law and say that VID over 2 is just this voltage drop VGS1 minus this voltage drop minus this voltage drop. So we're just applying Kirchhoff's voltage law around the input loop. And so from that we get let's see, VID over 2 is equal to VGS1 minus VGS2 minus VID over 2 is equal to 0. And from this, we get VID is equal to VGS1 minus VGS2, which we can write as VTH1 plus the square root of ID1 over K1 minus VTH2 minus the square root of ID2 over K2. If we assume transistors M1 and M2 are perfectly matched, VTH1 and VTH2 represent the same quantity. So these two terms exactly cancel each other out. K1 and K2 will be the same thing. So we'll just replace it with a single K. And what that gives us is the differential, the input differential mode voltage, VID, is equal to 1 over the square root of K multiplied by the square root of ID1 minus the square root of ID2. Here we're going to have to do a little bit of manipulation, okay? So as a quick aside here, on the right, I'm just going to give myself some room in case I need it. We know that ISS is equal to ID1 plus ID2. And we know that delta ID is ID1 minus ID2. So from that, we can say that ID1 is equal to ISS plus delta ID over 2, and ID2 is ISS minus delta ID over 2. If we substitute these relationships into this expression, what we find is that our input differential mode voltage now becomes 1 over the square root of 2K multiplied by the square root of ISS plus delta ID minus the square root of ISS minus delta ID. What we are looking for is a relationship where delta ID is a function of our differential input voltage.
Why is the 200 removed?
So we have a factor of 2 underneath both of these square roots that's common. So when I pull it out, it goes there. No problem. This algebra is a pain in the ass. Yeah. All right. So what we need to do right now is to figure out how to get rid of all these damn square root signs because they're making everything hard. That's pretty much what we're going to do, okay? So what I'm going to do is I'm going to square both sides, but I'm also going to get rid of this 1 over square root of 2K term by multiplying, bringing it over to the left-hand side effectively, so that I get 2K times my input differential mode voltage VID is equal to ISS plus delta ID plus ISS minus delta ID minus 2 times the square root of ISS squared minus delta ID squared. And obviously, this guy and this guy cancel. Sorry, that went slightly too far. And thus, this is equal to twice ISS minus twice the square root of ISS squared minus delta ID squared. And now we're just going to do some manipulation, right? So there's a common factor of 2 on both sides that we can get rid of everything there. So that's going to give us K times VID squared is equal to ISS minus the square root of ISS squared minus delta ID squared. So I can rewrite this as the square root of ISS squared minus delta ID squared is equal to ISS minus K VID squared. If I square both sides again, I get ISS squared minus delta ID squared is equal to ISS squared plus K squared VID to the 4th power minus twice K ISS times VID to the 2nd power. And now I can remove ISS squared from both sides and solve. And finally I get, delta ID is equal to the square root of 2K ISS VID squared minus K squared VID to the 4th power, or K times VID times the square root of twice ISS over K minus VID squared. And finally, substituting in 1/2 mu n C ox W over L for K, this gives me 1/2 mu n C ox W over L times VID multiplied by the square root of 4 ISS over mu n C ox W over L minus VID squared. So we are 90% of the way through here. There's a small problem, okay? This 4th order relationship here effectively means that if we plot this as a function, if we plot delta ID as a function of VID, what it's going to look like is this. So on this axis, we have delta ID. And on this axis, we have VID. And what we'll see, let me graph this real quick. Is something that looks like this, where effectively delta ID is approaching 0 as VID starts approaching plus or minus 4 ISS over UN Cox. Right. So when this term starts going to 0, that means our difference in our currents also starts going to 0, which can't be true. So the error that we have here is that we are assuming both transistors are always on, and we know that's not the case. When VN1 is very, very large, only transistor M1 is on, M2 is effectively turned off, and vice versa. When VN2 is very, very large, only transistor M2 is on, and transistor M1 is effectively off. So if we analyze this circuit where ID1 is approaching ISS, then we know M2 operates at the edge of conduction while M1 is carrying all of the current. So at this specific point, VGS1 looks like VTH plus the square root of twice ISS over UN Cox W over L, and VGS2 simply looks like VTH. From this, we can see that our input differential mode signal also has a constraint on it. It can't get too large, or we start getting into those weird spots. And so our input differential mode signal can only be 2 ISS over UN Cox W over L, or root 2 times VGS minus VTH. So there's a relationship between the largest value our input differential mode signal can have versus our input differential, or excuse me, our input common mode signal. Luke.
What is that first one? Does that say VGS1 equals VTH? Like, what does that say?
VGS1 is equal to VTH plus square root of 2 ISS over mu n Cox W over L. So let me go up here real quick and explain exactly where that comes from. It's literally this guy where ID is all of this tail current ISS. That's it.
Yeah, is that an and or a plus? What is the VPN? That just.
Sorry, okay, so this guy right here is a plus sign, this guy right here is an and. So this is telling us what VGS1 is doing, this is telling us what VGS2 is doing. Sorry for my shitty notation. Okay, thank you.
I was like, is that one?
So this is a plus sign, this is and. Let me write that out.
Two different equations.
Yes, two distinctly different things. Thank you. I understand where the confusion is.
I'm starting to doubt myself. It's like, all right, we added twice of something, but it's still equal to itself.
No, that's my shitty notation. I apologize for that. Okay. So at this, what I'm trying to say here is at this very specific point where transistor M1 is carrying all of our tail current ISS, this is telling us what VGS1 is. This is telling us what VGS2 is. And from that, we can see that our differential mode signal is the difference of these two, right? So the maximum value that our differential mode signal can be is the difference of VGS1 and VGS2, which is this guy right here. And it happens to equal the square root of 2 times the maximum value that our common mode signal, our differential pair, the maximum common mode signal that our differential pair can process. So from this result, our differential output voltage VOD, which is negative RD times delta IB, becomes negative 1/2 mu n Cox W over L times VID RD multiplied by the square root of 4 ISS divided by mu n Cox W over L minus VID squared, where the magnitude of VID max is given by the square root of 2 ISS mu n Cox W over L. And without redrawing this, I'll come back to this equation in just a second. Effectively, what we're going to see our output voltage do is swing between this point and this point. So it's just cutting off those tails where it looks like our drain current starts, our differential drain current delta ID starts going back towards 0, because that literally doesn't make any damn sense. Okay. So we're just bounding it between here and here. All right. So that's enough out of me for today. I feel like I've confused you enough. What we are going to do on Friday is we're going to do our small signal analysis for both the BJT case and the MOSFET case, where we're going to spend the overwhelming majority of time talking about BJTs and then go for MOSFETs, R pi is infinity. And so this gets easy. And then we get into funky stuff on Monday.